sitting here at 2,600 meters in Bogota, overlooking buildings and mountains and electricity, to talk about light. Now, first of all, we can ask, what does light tell us? Well, we see the mountains. The mountains are far away. The light is transmitting information from the mountains to us. We can see it. Light is also EM waves, so electromagnetic waves. And light is transmitting information that we can't see. So there's all sorts of stuff coming off the mountains and we can't see it. But if we had certain detectors, we could. Now, light has had many different theories, and starting in the mid-1600s, we really understood that light was a wave or light was a particle, and back then it was or. Newton thought it was a particle, Huygens thought it was a wave. Now, by the end of the 1700s, we basically had lived in a world where Newton's idea that light was a particle was the major view. But by that time, we also understood the phenomenon like refraction, reflection, and diffraction and interference with what was then called the corpuscular theory of light. That light was indeed a wave. So, we then got into a century where light was a wave. Now, in the mid-1800s, we had an issue. Because if light was a wave, then what did it travel through? Sound travels through air. The sound of my voice is traveling through air. Water waves travel obviously through water. Okay, so what do light waves travel through? Because obviously it's a problem. We can see the stars. We can see our star, which is the sun. We can use a telescope and see other planets. We can see the moon. So what is light traveling through between them and us? Now, the theory was that it was an ether, and that there was something emanating throughout the galaxy that was allowing light to travel as a wave. In the mid-1800s, Michelson and Morley, two researchers, tried to test this theory by measuring the speed of light. Now, at that time, we kind of understood that the speed of light was constant, was that if the speed of light changed, then there would be an ether. Imagine it this way. When I flew here, there was a tailwind, so the plane went faster. When I fly back, there is a headwind, so the plane flies slower. So as the Earth rotates around the sun, probably the ether is going to be going in one direction at one point and in the other direction at the other point, so light would be slower and faster. We did not understand at that time the speed of light was constant, but we did understand that speed was dependent and relative. These researchers measured the speed of light in many different ways and did not find any difference. They always found the speed of light to be the same. Later on, other researchers tried it differently, and this again is the mountain, because one of the most famous experiments was done at the top of the mountain to see if that affected the results, and it didn't. So things were done more accurately and more accurately until we found that there was no ether. So then we had a problem with, okay, we have a wave that is light, but it has nothing to travel through. How does that work? Another thing happened around 1900 with Einstein, Albert Einstein, where he shot light, and the theory before was that light was a wave, because that was what was predominant at that time, and a wave should act in a certain way. But when Einstein shot light at the atom, this was not the behavior. Specifically, what he was looking for was that all wavelengths or all frequencies would eventually eject an electron. But what actually happened was the electrons were only ejected if there was a frequency met, a threshold, and lower frequencies wouldn't work. This was very confusing to everyone. Is light a wave? Is light a particle? At that point, we no longer knew, because refraction and diffraction couldn't be a particle. But Einstein's so-called photoelectric effect couldn't be a wave. So what we get to in the beginning of the 20th century, 100 years ago, was the idea that light is both a wave and a particle, and it depends on what you are doing. In reality, light is a feature of a force called electromagnetism weak, or the weak electromagnetic force.